pleasure to welcome here the Dr. Katarzyna Kruszyńska, who defended her PhD here at our observatory. She's now at her postdoc in California in Las Cumbres Observatory. And Katarzyna is working within the Omega key project that is a preparation for LSST Rubin. And she's gonna tell us about this project and the result that she obtained recently during her talk. I hope everything works, and the floor is yours.
Thank you, thank you. Let me just check if where is it pointing? Oh, the middle. Okay. Okay, hello everyone. I'm very happy to be here because I haven't been in Warsaw Observatory since my defense, at least in this room. And today I would like to talk about a new thing that I've been working on for the past year. And this is a little bit of an exploration type of presentation, so please bear with me. But I hope that you will find it very interesting. The title of the talk is Preparing for Rubin and Omega Key Project as a Pathfinder for LSST. So, oh no, okay, sorry. Okay, it works now. This is what I'm focusing on pretty much, and like this is what majority of astronomers are focusing on, especially people who are interested in the Milky Way. And in here in this image, we have everything that we can observe because it's emitting light. However, there are certain groups of objects that are extremely interesting, especially in the recent years, that don't necessarily emit light. And without having observations of those, we cannot really properly understand how our universe works. And for example, how did the solar system come to be? And these things are brown dwarfs, planets, and black holes. All of these things do not emit light. Maybe planets can reflect a little bit of light, but we have to like sit in the solar system to observe them, or use some more advanced techniques. But in terms of for example, for black holes, we can maybe observe them if they have a companion and they're doing something with the companion, for example, accreting it. However, like there's also a whole bunch of solitary black holes that we cannot really observe because they're just flying through space without interacting with anything. And this is where microlensing can come. Oh, sorry. This is the current census of dark remnant mass distribution. By dark remnant, I understand white dwarfs, neutron stars, and black holes. In this plot, I depicted different types of observational techniques we can use to observe them. In pink, we have, in pink here, you barely see the colors. In pink, the largest populations is the white dwarfs from Gaia data release 3. And then sufficiently smaller populations of gravitational wave binaries with, like, you can barely see it, but here in gray, the final mass of the merger is depicted. The earliest observations of neutron stars and black holes, which are pulsars and X-ray binaries, depicted in here, with two mass gaps that we observed, which is the first mass gap in here between the heaviest neutron stars and the least massive black holes, and also theoretical second mass gap where for instability supernovae should occur. Another census of our knowledge is the exoplanet distribution. This is a little bit, parts of this plot is a little bit outdated, but this is the exoplanet distribution created by Matthew Penny in 2019 for a Roman upcoming NASA mission. With here in barely visible in red dots objects detected by Kepler, and here in blue we have the sensitivity of the Roman space mission for different types of planets, and in black dots we have like different types of techniques of observed planets. As you can see, majority of the planets that are in our solar system are actually not observed so far. However, Roman is going to change that. And this is also something that we can get out of the upcoming mission called, the upcoming survey called LSST, which is a survey operated by Vera C. Rubin Observatory. It is a joint, it's a joint mission between the U.S. National Science Foundation and Department of Energy, and it is operated, well, it's actually already built and operating. The commissioning phase just finished. The first commissioning phase. The observatory is located in Cerro Pachón in Chile. It's a 9.4 meter Simoni survey telescope with the extremely huge 9.6 square degree field of view. It will provide multi-band photometry, and it will go pretty deep until down to 23 magnitudes, kind of depends on the filter in the galactic plane. However, because the telescope is so huge, it will saturate at 16 magnitudes. And the main objectives of Vera C. Rubin is, and LSST, which is the legacy of space. Legacy of yes, yeah, thank you. It's been changed in a couple of last years. So LSST's main objective is mostly located towards like dark energy and dark matter, which is pretty much outside of the galactic plane. But also it will focus heavily on creating inventory of solar system objects, including detecting objects that are coming from Oort cloud or even further, or even beyond. It is also going to map the Milky Way on a very deep, unprecedented scale, and also it's a transient mission. It's going to explore a lot of different objects that will change position and brightness over time. This is pretty important plot, which is the survey observing strategy, and I wanted to show this because in the recent years, LSST wasn't supposed to observe galactic plane, but it will. It will be observing a galactic plane, which is very important for here depicted in what is this color? Violet. It will not be avoiding galactic plane, even there are some regions which will be probed a little bit more densely than previously expected, and this is pretty important for my case, which is microlensing. I also invite you, especially for people who are interested in microlensing, I invite you to read the Natasha Abrams paper, which recently was published. It provides a more in-depth analysis of what type of microlensing events we will be able to observe. Okay, so this is the introduction to microlensing slide. Who has never dealt with microlensing in here? Never. Yes, never. Okay, so I'm looking on this side. Have you ever done microlensing in your life? Yeah. Okay, good. So I can skip this now. I'm joking. I will give a short introduction to microlensing just to be on the same page with everyone. Gravitational microlensing, as you probably know and hear in this observatory, is an effect of Einstein's general relativity, where we have a massive object, which is the lens. It's passing in front through the line of sight of a distant source, and because the object has mass, it distorts the space-times around it, which causes a slight shift in the position of the observed source star, or quasar, or galaxy. In case of microlensing, the lens is located in the Milky Way or in its neighborhood, but the principle is pretty much the same as strong lensing or weak lensing, if you're more familiar with that. The one thing that we have for free from microlensing is that because the lens is pretty near to close to us, we can observe the change of the brightness of the source in time. And this is the way we detect it instead of like looking for distorted images. And finally, it works. Okay, so this is a very short summary of how it works. We have on the left-hand side, we have the photometric effect. On the right-hand side, we have the astrometric effect. The astrometric effect is an effect where we because during microlensing, like during any type of gravitational lensing, the image of the star or the source is split into at least two unequally magnified images. The centroid of light is going to shift, even though we don't have like the resolution to split them. In the majority of cases, we can still, with very precise astrometric instruments, we can observe the shift of the centroid of light. And seen on this slide, there's going to be a slight deviation. Obviously, if the source is passing, or the lens, they're passing relatively close to each other in terms of like angular separation. We will also see an observable photometric effect, which is a very unusual type of brightening. It's very if we have a perfect light group, it's going to be very smooth and very symmetrical in most of cases, which is kind of hard to confuse with other types of phenomena if we have a perfectly sampled light pattern. I will also introduce here a term called PSPL. This is point source point lens, because it's going to appear. This is basically the simplest type of microlensing you can have, where you have a single lens, single source, and because of reasons you can assume they are point-like objects. We also have, and this is like where majority of microlensing research is going on, we also have anomalous events. For example, events with a planetary anomaly, when we have like the main event, and then something else is appearing, like we have at least one more peak. Or we have something called a microlensing event with parallax effect, where we have a single lens, single source. However, the time scale of the event is very long, and we see these characteristic wiggles or asymmetry caused by the Earth's movement around the sun. And I will stop here with the explanation of types of microlensing events. And I wanted to like tie in those two topics together by presenting the scientific drivers that for our project, or like majority of people involved in microlensing LSST, which is to find hidden populations that I mentioned at the beginning of the presentation in the Milky Way. We want to uncover exoplanets, brown dwarfs, but because of LSST and its cadence, as going back to the slide with the survey strategy, because LSST is not going to probe the galactic plane as often as, let's say, a typical microlensing survey would, which is like every day or every couple of hours. We mostly want to detect the compact objects, which are black holes, hopefully. And LSST is going to provide us with multi-band photometry very deep in the galactic plane and the wide coverage of the galactic plane. However, LSST will not provide, as I mentioned before, high cadence observations, which means we are not able, with LSST photometry alone, we won't be able to properly characterize microlensing events. Even events which which are long duration, they will last for like a year or two. With LSST light curves, they're going to be patchy enough to allow for many degenerate solution and like uncovering the system that has caused like the lens and the source that have caused these events is going to be very, very, very difficult. And this is why we need follow-up observations. And this is where comes the Omega Key project. It's a Las Cumbres Observatory key project, which is a key project. Is in this case is a project which was identified by Las Cumbres Observatory as ideally suited for the network. Actually, does anyone have, how much of you know what Las Cumbres Observatory is? Okay, a small bunch. Okay, so sorry, rewind. Las Cumbres Observatory is a network of robotic telescopes. I will show you a map in a moment. They're located all around the world, and they, in principle, can provide you with a 24-hour coverage of your event. How often you can observe that event, that's a different story, but like what is the cadence? But in principle, you can cover it for 24 hours without human intervention. Well, you can, the telescopes are robotically operated, and there's very minimal like intervention from a human on that side. The LCO key project is a project where which is very well suited towards the LCO facilities, and it is like maybe pushing the science forward. In this case, we are focused on observing microlensing events, and currently we are in that's the 5th year of the project, if I'm counting correctly, which the first phase of the project focused on exoplanets, and currently, because we're preparing for that, we also included additional science goals, which is detecting or observing brown dwarfs and black holes. And we have been awarded with a significant portion of time on the telescopes. There is the map. This is the map of LCO facilities. There are only two meter telescopes, which is going to be important in a second, and several. I want to say like, I don't know how to count, but there's several 1 meter telescopes which are like workhorses of for our project. In order to operate our observations, we are using something called microlensing observing platform. It's a target operations manager, which is a link between surveys here and the facilities that are going to conduct the follow-up observations on the events coming from the surveys. And here on the left-hand side, I have presented the expected numbers on the amount of alerts, whatever that means, coming from here from LSST. This is from ZTF, and this is from OGLE for comparison. So in principle, OGLE produces roughly 1,500 microlensing events each year. And there is like this very old floating number, which is 10% of those are supposed to be anomalous, and 10% of the anomalous are supposed to be planetary events. So if we scale this, the events that we get each year from OGLE, we expect well, pretty much 15 planetary events from OGLE. But if we scale this up to expected numbers from LSST, which might be even 10,000 microlensing events per year, we will end up with 1,000 anomalous events and 100 planetary, which is very difficult to model. But also, if we want to model it properly, we need a lot of follow-up data, and also triggering observations for this amount of anomalous events is unfeasible for humans, in my opinion, and this is why we need some tools, some programmatic tools that will take a lot of work from my shoulders and my colleagues' shoulders, and move them and just operate this by an algorithm. Okay, so for LSST follow-up, we will need consistent, in order to properly model microlensing events, we will need consistent coverage. We will have to cover anomalies, which can happen from minutes to hours, like in case of planetary and brown dwarf anomalies, up to like days or even years. We will need multi-band photometry to get the color information, and also to use the LSST data to the fullest. And we will also need, in many cases, additional information, which is, for example, source distance, extinction, and source type. Without this, we will not be able to recover, for example, planet mass or lens or the black hole mass. In the galactic plane, the source distance is unknown because if people are familiar with microlensing, you cannot really use the methods of, by the red clamp method. But it's significantly less crowded, which means the blending is going to be lower, and we will not struggle that much with, for example, with observing targets in this region with other telescopes. On the other hand, in the galactic bulge, we can assume the source distance. It is an extremely clouded field, and it's also extremely reddened, and this is a problem for us. However, in the Omega Key project, we are trying to our best, and we are running on very limited human resources. So we started tracking two types of events, which are candidate planets, which last, as I mentioned, for hours or days. And we also track now, this is a new invention for like a year and 3 months, pretty much. Now we also try to track long duration events, which are candidates for like dark remnants and can last even for years. We apply for each event that we ingest from a survey that I shown before, like OGLE or ZTF or Gaia, for example. For each event that we identify as a candidate microlensing event, we apply two types of priority numbers, corresponding to either a candidate planet or a candidate long duration event. We also use photometric follow-up with different types of facilities. Right now we are using Las Cumbres Observatory, obviously, and also through our colleagues from Brazil and Argentina, we have access to LCO Observatory, which is located in Argentina. And this allows us for a better coverage of the event, which will, if we are lucky, the weather and the moon are not obstructing our observations, we can fully characterize the system, hopefully. We also, for many sources, we conduct spectroscopic follow-up, either with the LCO Floyds telescopes, which are Floyds is mounted on 2-meter telescopes, or with SOAR telescope, which is a 4-meter telescope in Chile. And in that case, we use a Goodman high throughput spectrograph. I think that's the name. And through observations of those, we can get source type, extinction, and distance code. Again, this is pretty difficult. We are also tracking transient events, which means that we have to constantly update all of these things, especially the priority and the request for photometric follow-up. I don't have to do this. Also, and now coming to LSST, LSST follow-up is going to be, will be conducted with different facilities, because in case of microlensing, you can, especially coming from LSST, some of the events are going to be very, very dim at 23 magnitudes. I don't know, I think you have to use a 6-meter telescope to observe that. But on the other hand, some of them can be high magnification events, which will suddenly jump up to even like 9 magnitudes, and then you cannot use a 2-meter or 4-meter telescope, or like 1 meter. It saturates too quickly. You have to like jump to 0.4 meter, for example. And this is all doable and and already parts of this is already encoded into our system. which means we can like switch without human intervention programmatically between small telescopes and large telescopes depending on the brightness of the follow event. In case of LSST, I am a little bit worried because of the like with telescopes this large and so survey going so deep, we will need definitely larger facilities than just 2-meter LCO telescopes or 1-meter LCO telescopes. That's why SOAR is already included into this network, into something called EON network, which is Astrophysical Events Observations Network, which is basically kind of like the idea behind this is basically to have LCO capabilities, but without LCO telescopes. And LCO is currently working on including, LCO has been working for many years with SOAR and Gemini through this EON network, but also soon Blanco telescope, which is 6-meter, I think, is going to be included. Is going to be capable of receiving programmatic requests and then executing them. And there's also several other telescopes that are recently we received we received funding to provide programmatic access to the programmatic and API access to those facilities, which I find very exciting. And this is the structure of how MOP works. We have surveys and alert brokers, whatever that is. For example, maybe you're using Think, maybe you're using Clarity or some other alert broker. If you're familiar with GTF alerts, we harvest them automatically without human intervention into MOP. I mean, you can always add your target manually, but that's not really what we are doing. Why we are doing this? We automatically classify some subset of the events. In this case, Gaia events, because Gaia does not provide any type of classification. Then we automatically select targets for observations. We automatically submit observation request into telescopes, which are robotically done, and then the information is sent back to MOP, which is also doing modeling of the events, again, without my intervention. And ideally, this system just runs without any problems. And the only thing you have to do is just check every day or every couple of days if you have any interesting targets, or even every half a year if you're super lazy. These are some examples of the events observed by Omega in recent years. This is one very nice. Both of them are anomalous, yeah, there's some data from Omega in here, but also from Gaia or a Danish telescope. And now I want to move towards the topic of this talk, which is the lessons from the Pathfinder project. And this is something that I learned in the last year when I was working on Omega targets, and also like having in the back of my mind the fact that LSST is coming very, very soon. As I mentioned before, it has finished commissioning phase with the ComCam now. And next year, by this time next year, there should be some alerts coming from LSST, I think. So this is coming very soon, and I don't really feel prepared, but that's maybe I'm just too pessimistic. So this is what I found out while doing this project. First of all, targets coming from microlensing surveys are usually pretty good in terms of classification. However, and we can treat them as microlensing candidate events. However, this is not true for Gaia or ZTF, and also LSST, which will not provide any type of classification. It just releases that something changes its brightness, and you have to deal with it on your own. Additional thing that I found out is that even though we might get some type of classification somewhere, or we like think that the target coming from a microlensing survey is like the stream of alerts coming from a microlensing survey is pretty good. There is still some need for additional classification because microlensing is pretty rare compared to many other phenomenon, and a lot of things are blowing up. And if you don't have a very well sampled light curve, you can confuse them with microlensing. You can even confuse a supernova going off if you're not careful enough. So, for example, on the left-hand side, we have something which is not microlensing. Looking at the time scale, 2000 days, doing little wiggles. And on the right-hand side, we have a very beautiful microlensing event. And the way I have to design the system is to be able to distinguish between those two types of events. So, for example, check if the model is fitting correctly, or check if, I don't know, maybe there's some color information, or the timescale is completely insane. Currently, we are relying on, in terms of classification, we are relying on catalogs of variable stars and extragalactic sources, for example, quasars or supernovae. And if you have your favorite catalog and you're thinking about publishing it, and you think it's gonna be extremely important for microlensing, for LSST, providing programmatic access to it, for example, through TAP protocol, which is with which the Python package called Astronomical can work. If you can provide that, that would make my life so much easier and happier. So yeah, this is a little public safety announcement for me. We are also using transient name server because they do provide classification because of their rules that they have. So if there is a spectrum and they classify a transient, they get a classification spectrum. It's already classified, and then you can just send a little request to the transient name server, and then it will respond to you with, oh, this is actually classified as supernova type 1A or something. And there's also quality checks that are relying on the microlensing model fit. For example, if the chi-squared value is too big or not, or if we got sensible numbers for baseline magnitudes and other things. But this is still a little bit of work in progress. However, some of LSST brokers are going to provide classification. So the alert is coming from LSST will go through the broker. The broker is going to do its magic on it, and then it's gonna spew a bunch of information, including a label. For example, we think this is most likely an R library, or we think this thing is actually a microlensing target. So we can use already those things for target selection. However, there is a question, how well will they be able to classify microlensing events, especially in the early years? And how well they will be able to handle contaminants, and also if there's going to be a process for a feedback loop coming from the community. So if community keeps saying oh, actually you have to change your classifier because these types of objects are, I don't know, PE stars, or these types of objects are actually Lyrae or Miras. So, and they've been classified as, I don't know, microlensing or supernova. So that is a question that you have to keep in mind, and also people involved in LSST are in talks with the brokers for LSST. We also, because we want to do we are doing our automatic target selection. I have noticed that it's already important, even though we, for example, overproduces 1,500 microlensing events each year. This is already a pretty huge number of events to be selected and followed on. if you're trying to do it on very, very limited human resources. And actually, the target selection we have works pretty well on a subset of cases, and this is an example. This anomaly in here was selected. I can barely see it, but you have like these green points and blue points. These are points coming from LCO. This target was, I didn't know that there's a planetary anomaly going at the time. I just came in like I don't know, a few weeks later, and I noticed that, oh, actually, this is a very interesting microlensing event with a planetary anomaly, and we have very nice data for it. However, even though the planetary anomaly follow-up target selection is pretty good, and we're pretty happy with it, the introduction of the long duration follow-up events is not very well understood, and it has resulted with a very long list of candidate events with insanely large timescales, and I am just trying to figure out how to deal with it. And the way to deal with it is to get a robust microlensing model, a PSPL model in this case, because we have a that's microlensing event coming from Gaia, but it also has some data from we also have some follow-up data for it. And here I introduce my greatest enemy blending, which results in this very, very large timescale, especially because of the model is not very stable. Third thing is, because we have to do it all the time, every time we get a new point, every time we want to request observations, everything has to be done automatic and robust, and our microlensing models have to be computationally cheap. Which means I want to have a single model fitted within minutes and no longer, because otherwise it's going to be too costly in terms of, for example, if you're using cloud resources for your computational things, it's going to be expensive and it's just not feasible. Another thing that I have learned, it was very painful this year, that if you're conducting follow-up observations for a microlensing project, you will suddenly find out that your data is taking a lot of space, like storage space. If you have hundreds or thousands of images per target, this is gonna end up with it's gonna just, you need storage, and ideally maybe moved to cloud, because I think it's a little bit more robust than a physical disk sitting somewhere. But another thing that we've noticed is that we have follow-up data. We don't want to have a human sitting there and like checking if the images are good and everything, because you have thousands of images like that. So this has to be done robustly without human intervention. And this is difficult. Another thing that I have, I've learned also from my PhD on Gaia is that if you're observing targets in the galactic plane, you don't really know where your source is located, because you cannot assume that majority of the clouds are in the red clump, and the red clump is in different places. You might try to use Gaia distances, but they may be biased for a multitude of reasons. And also in terms of, this is also something that I learned from Gaia, in this case, not only from Omega, but if you have a survey and it's in its early years of observing, you need spectra to confirm the classification that you have. And like maybe, not observe hundreds of BE stars. And finally, is this the final slide? Hopefully. Yes. This is the summary slide from my lessons for LSST. So I think I can just leave it here, unless you want to see the map of the events that we have from MOP. These are all of the events that have been selected for observations a couple of months ago. 109, it's not so bad. And I will just leave you with this slide, and I think I will take questions.
Thank you. Thank you, Katarzyna, for our talk and to make it on time. Do we have any questions or comments? Przemysł.
Okay, so two questions on the comments.
Mhm.
My first question is about the number of microlensing events that you follow up.
Mhm.
How many events do you observe? How many events come from OGLE and and Galactic service? How many events come from Gaia Science Alerts?
Well, for ZTF, we don't really have currently any type of good way of selecting microlensing events because none of the brokers have like a robust way of providing us with targets. So the only way we get microlensing events from ZTF is like if we find it ourselves somehow and we like check it manually. Majority of our events are actually coming from OGLE, and many of them, the ones I think a whole bunch of them that we follow on are coming from the new thing from OGLE, which is events from the galactic plane. We have, because of reasons, because there is an additional key project using LCO for following microlensing events in the galactic bulge. We are not observing the innermost, the high cadence zone of microlensing. So, for example, we don't follow KMT-net events, but like a huge, like a bulk. I want to say like, especially also with Gaia being like slowly dying, slowly approaching its end of its lifetime. I think like, let's say 80% of targets are actually coming from OGLE. Yeah.
Okay, so another question about the task question about the strategy, LSST observing strategy in galactic bulge. You said that LSST is going to provide 10,000 microlensing every year, but this is because assuming perfect cadence.
Yes.
As far as I understand, the plans are that the cadence in galactic bulge will be low. I mean, one observation every few weeks, which is not sufficient to detect the microlensing test. So, do you have any insights about that?
Well, so in principle, and this is a result from Natasha Abram's paper, we kind of like, we are not really interested in events that are shorter than 20 days, because with any type of survey optimization, LSST kind of won't be too sensitive for it, or it will result in like cutting time on other science cases. We are strongly pushing for having still a decent cadence in the galactic plane. I am not sure how much LSST will focus on galactic bulge, because they're kind of a little bit worried about crowding. Well, on the other hand, I think it would be a pity to not observe there, especially with Roman coming up online, which will focus heavily on galactic bulge. And I think, like, for example, combining those two surveys is going to result in amazing scientific results. We are trying to inform decent cadence in the galactic plane and galactic bulge. However, I'm not sure how much it will change from the current version. My understanding is that the version, the fourth version, the 3.4 baseline is pretty close to what is going to start. However, there is a very important caveat that the survey optimization committee has told us. They're going to change the survey strategy even during the operations of Rubin. So I don't know, maybe not everything will be lost. Yeah.
Okay, and the last thing I would say is that whenever you have at a very early stage, when you see the rising graph, the models will be very uncertain, the parameters you get are very uncertain.
Yep.
Especially you get this. If you have a correlation in the time scale, landing the parameter, that's very.
Yep.
But unless even this, if you can measure
yes.
that, what you can do is to use a two-parameter model from Google.
Yep.
You should have that. It's my suggestion.
Yeah, I think that's something that I was considering because I'm also currently developing a modeling pipeline that will that in principle is supposed to be plugged into any project that we want to use for like modeling hundreds of microlensing events. And I didn't use the parameter model, but I am more and more convinced on using it, and I think it's very cheap. So I think
It's cheap.
yeah.
It should work well.
Yeah.
For example, like
Yes. Yes. Yeah, and yeah, thank you for that. I'll include it at least into like some development branch. Yeah, I know that there are also people trying to use it for at the stage of classification, like at the broker stage, because that's also where it's very powerful.
There is one question on Zoom.
Yeah, I would ask, is the Omega project designed only for the LCO telescopes, or can other observatories such as Astronomical with smart telescopes be included in the network, like in the quantum system?
Yes, they can. If there is a, well, I mean, in principle, if we have the system, because we are working very closely with the black hole TOM people, if, for example, we can somehow send you a list each night of targets to observe to Ostrowiec, and then you can like use them for your stuff, and then you upload the data somehow to us. Yes, definitely we can work together. In this way we work with the LCO Observatory with, I think the telescope is called Leoncito, where we provided the observers some tools, and then they go to our target observation manager to MOP. They can go to the website, and from there they can select targets that are visible from their site, and they can like select them based on some things. But I think ideally it would be just we provide you with a list of targets that you can observe, and it's like I know each night you receive an email or something, and then we get the data and everything is nice. So it's not limited to LCO only.
Thank you. Any more questions, comments? See, so thank you, Katarzyna. Thanks for So next seminar is on the 7th of January. We'll have Christian Ilkiewicz talking about symbiotic binaries. And tomorrow at 3 p.m. there is a Christmas meeting, so everyone's welcome and invited. Thank you very much.
Thank you.